Hello, and welcome back to the course. So today we're talking about Hurwitz theorem, which is subsection 5.4.3 in the book, and you can get the book in the link in the description. All right, so let's just get to the theorem. It's state Hurwitz. So suppose that we have an open set U in C, right, in the complex plane, and suppose that we have a sequence of holomorphic functions, and they converge uniformly on compact subsets of U, of course, to a holomorphic function f. And now suppose that gamma is a cycle in U, and let's suppose it's homologous to 0 in U. And if you remember, that says that means that gamma does not wind around any point in the complement of U. So it doesn't wind around anything outside of U. Furthermore, suppose that gamma doesn't actually wind around anything more than once, or it doesn't wind around anything in the negative direction or something like that. The winding number around anything that's not in gamma, any point that's not in gamma, is either 0 or 1. Right? So that way we can talk about the inside of gamma, which is the points that gamma winds around. We're going to call that V. Right? So now suppose that f has no zeros on gamma. That's important. And it has exactly k zeros inside gamma. So in this V, in this set where that gamma winds around, right? So it has exactly k zeros inside gamma. Now, that means that there exists a capital N, some integer capital N, such that for all little n bigger than capital N, f sub n has exactly k zeros inside gamma. So k zeros inside V. And these, when we say k zeros, we're of course talking about counting multiplicity. So like z squared has 2 zeros, right? All right. So let's prove this. Basically, it says that if we converge to something, eventually all the things in the sequence have the same number of zeros. All right. So let me move a little bit, but same number of zeros, in some region. All right. So gamma is compact, right, as a set. So that means that f being continuous, right? I mean, it's holomorphic, so it's continuous. So it achieves a minimum, right? Well, that minimum can't be 0 because f is not 0. Well, I mean the modulus of f achieves a minimum. And that can be 0, can't be 0 because f is never 0 on gamma, right? So therefore, there is some positive delta that's strictly less than the modulus of f on gamma, right? All right. Now we have that f sub n converges uniformly to f on gamma, right? F n converge uniformly on compact subsets. Gamma is a compact subset, right? So, all right. So what does that mean? That means for n little n large enough, we have that the difference between f and f sub n is less than delta, right? That's just by uniform convergence. And well, we know that is always strictly less than f, the modulus of f. And so therefore, we get this inequality, f minus f sub n, modulus of that is strictly less than modulus of f. And that really looks like something that you would use in Rouché's theorem, and you use that in Rouché's theorem. And Rouché's theorem tells you that f and f sub n have exactly the same number of zeros in V, right, inside this gamma, right? It's basically just applying Rouché's theorem, right? All right, just a sort of a different different version of of this this result that we've been doing for a while, right? All right, so now the no zeros on gamma is a necessary condition, right? Suppose that you have gamma is the boundary of the unit disk, and take an f which actually does have a 0 on the boundary, z minus 1, right? That has a 0 at 1, and then we take this f sub n that converges uniformly on gamma to f, right? converges uniformly on all sorts of sets. But on any set, right, converges uniformly on C. This guy, the f sub n, inside gamma, it always has 1, 0, right? Because it has a 0 at 1 minus 1 over n. That's inside the disk, right? That's inside V. But F has no zeros inside, right? So it doesn't have the same number of zeros. That could also be that the 0 could be outside, right? We could F sub n could be 1 plus 1 over n and comes from the outside. Well, then inside has the same number of zeros, right? So, but if the 0 is on the boundary, well, f sub n could have zeros that's inside or outside, right? You can't quite decide. That's the point, right? So we really need f to have no zeros on gamma to make this to make the statement of Hurwitz's theorem. All right, so let's do like a really sort of stupid example. So let's suppose that we have we take n integer k, right? And then we're looking at this these polynomials for large enough d, right? So there exists some capital N such that for all d big enough, so for all d bigger than capital N, these polynomials have exactly 2k zeros in this disk of radius pi k, right? It might seem a little sort of arbitrary, but it seems like that might be hard to exactly say, right? How would you necessarily prove it sort of without having all this machinery, right? Well, with having all this machinery, well, it is the the partial sums of the power series of cosine, right? That's what you might recognize here. And cosine has exactly 2k zeros inside this disk, right? So therefore, these polynomials for large enough d have to have exactly 2k zeros. Now, you might say, well, obviously because cosine has 2k zeros, but if this was just sort of in the real setting, right? If these weren't holomorphic functions, you wouldn't be able to say that, even if it was things that have power series. So this is actually, it is quite powerful, but this might seem a sort of a contrived example, but yeah, it's an example. All right, so the usual application of Hurwitz's theorem, or at least the usual application that we'll see, we're taking a small disk, right? And basically, what we want to show is that if we take a 0 of f and we take a small disk around it, or 0 of some multiplicity, right? And if we have a bunch of functions, sequence functions converging to f, then eventually they'll have the same number of zeros in that small disk, right? That's exactly what I'm writing here, right? So suppose that we have a sequence fn converging to f, right? And suppose that we have a 0 of f of some order, right? Then for a small enough disk, right? Basically, we take a disk, such that it's the only 0 of f inside that disk. Then, if we go far enough in the sequence, then the functions in the sequence far enough will have exactly k zeros counting multiplicity. So maybe it's a 0 of order k, maybe it's k distinct zeros, maybe it's some mix of that, right? But k zeros counting multiplicity inside that disk, right? If you want them to be closer, maybe you have to go further in the sequence, right? All right. Now, Hurwitz's theorem does not work for real functions, right? I said so much just a moment ago. Let's give an example. Let's give a simple example. Let's look at x squared, right? So the parabola, right? So that thing, just as a function of real variables, so function from the reals to the reals, right? F of x is x squared, right? Just plugging in real x, right? So that has a 0 of order 2 at the origin, right? The only place where f of x is 0 is when x is 0. Well, now take a look at x squared plus 1 over n, right? Well, those functions converge uniformly to f, right? But none of them have any zeros whatsoever, right? So Hurwitz doesn't work, right? And it's really, here it's because x squared is always positive, right? And we have nothing like that for complex numbers, right? There is no ordering for complex numbers, right? So if we look at the same function, but now plugging in complex, right? So we're looking at z squared, right? So we're plugging in complex z. We look at z squared plus 1 over n. Again, f sub n goes to f uniformly. That's still the same. The difference is just 1 over n, right? But now, if you look at this function sort of close enough, so for any epsilon, if I look at the epsilon disk around 0, eventually, for large enough n, z squared plus 1 over n will have zeros, 2 zeros, exactly 2 zeros, inside the disk. I mean, those, that's what they are, plus or minus I times the square root of 1 over n, right? So eventually, it will have these 2 zeros, right? So this guy is, z squared, well, and z squared, namely z squared plus 1 over n is positive, strictly positive on the real line. But you can see, the zeros, we do get zeros, but they're, in the complex plane, right? So they don't come up in the real line, they come up in the complex plane, right? All right. So for real functions, you cannot expect anything like Hurwitz's theorem, right? Nothing like this works, especially, not for, if you're just assuming uniform conversions. That's kind of a very weak thing to converge. Weak thing to require to say anything about zeros. All right, now let's look at an application of Hurwitz, right? And so look at an application to injective functions, and so. In complex analysis, there's always, there's a lot of sort of old school terminology that maybe isn't as used nowadays, but a lot of things that have other names now have sort of special names in complex analysis. So, injective holomorphic mappings are called univalent, right? Sometimes it's used even outside of complex analysis. It's univalent one-valued, right? So that's just injective. That's all that means, right? So suppose that you have a domain, you have a sequence of functions fn that converge uniformly on compact sets to some f. And let's suppose that, all of these fn's are univalent. They're all injective, right? So all the fn's are injective. So the conclusion is that f is either univalent or it is constant, right? Could be constant. It's possible for this, for this to be constant, right? Just think of, something like, z divided by n, right? And then, on the unit disk, well, you get uniform limit of z over n is just identically 0, right? All right, so let's prove this. So suppose f is non-constant. If it's constant, well, we're done. Suppose it's not constant, and so we have to show that f is univalent if the fn's were univalent. So what we're going to do is we're going to suppose it's not univalent. So suppose that there are two distinct numbers z1 and z2 in U, such that f of z1 is equal to f of z2. right? So that means that F is not injective, it's not univalent, right? And what we're going to show is that we're going to find an Fn which is not univalent. And so we're proving the contrapositive, right? All right. So now let's call this value f of z1, just this f of z2, let's call it w, right? And let's subtract it from f, right? So we have f of z minus w. That's what we're really looking at, this function over here. Now that has isolated zeros at z1 and z2, right? It's not, right, because f is non-constant, right? These zeros have to be isolated. Holomorphic functions have isolated zeros. So consider two disks, two small disks around z1 and z2, such that their closures are in U, particularly their boundaries are in U. Suppose that they're disjoined, and because S minus W has isolated zeros, we can assume if you take the closure of the first disk minus z1, S minus W is not zero there, and we can do the same thing for z2, right? All right. Now, mainly, we're assuming that F minus W is not zero on the boundary, right? That's really what we care about. Now, for a large enough n, and that means that Fn minus W has the same number of zeros in the first disk as F minus W, and we have the same thing for delta R centered at Z2. Right, so F sub n minus W has the same number of zeros as F minus W in either disk, right? Namely, there's at least one zero in either disk, right? Well, that means that there exists a Z1 prime in the first disk, maybe not equal to Z1, but it's in that disk, and a Z2 prime in the second disk, and these are different, different points, right? Because these disks are disjoint, and F sub n at Z1 prime is equal to F sub n at Z2 prime. They're equal to W, right? In particular, F sub n is not univalent, right? All right, so that proves the corollary. All right, so next time what we're going to do is we're going to look at the open mapping theorem. So holomorphic functions are actually very nice to the topology, even going forward, not just going backwards. They preserve open sets as long as they're not constant. Preserve open sets going forward, and that's the open mapping theorem is sort of a more a stronger version of maximum modulus principle in some sense. All right, so that's what we're gonna do next time, and see you then.